Hi guys, Miss Marusik here, and in this video we're going to talk about how kinetic and potential energy transformations can determine whether or not I have an endothermic or an exothermic reaction. Now, as a reminder, in our last video we talked pretty extensively about the differences between kinetic energy and potential energy. Kinetic energy is that energy of motion, either maybe the movement of molecules where I can measure the temperature, or light energy, whereas with potential energy, that's that energy of position, where I have maybe the structure of the bonds or the structure of the intermolecular forces that's determining the potential energy amount. The problem with potential energy is that I can't measure it or sense it. What I can measure are changes in potential energy that end up resulting in changes in kinetic energy. And so we're going to talk about the connection between those here. So just as a reminder of the first law of thermodynamics, energy cannot be created or destroyed, so our overall energy amount must remain constant for our process. However, we can transform between kinetic energy and potential energy. So let's say I'm starting off here with two hydrogen atoms. The issue with two hydrogen atoms is that they feel a lot of attraction with each other. They really want to come together. So when they're far apart like this, it takes a lot of energy, a lot of potential energy to help hold them apart. And so you notice here that in blue, that potential energy, the system is really large here. However, the kinetic energy amount, there is still some there. You still are going to have some rotations and vibrations in place. So there's still going to be that movement there. But when I let these come together and I release all that potential energy, what happens is that potential energy gets transformed into kinetic energy. So now you notice that kinetic energy amount dramatically increases. And that kinetic energy can then be released to my surroundings in the form of, say, light energy or heat energy. But the key thing here is that the total energy amount remains constant. So even though I'm transforming that energy into a different format, I'm still keeping that overall amount consistent. Now, the key thing about transforming energy is that it typically happens when I have some sort of bond or IMF changes that exist. And depending on what kind of change I'm doing will depend on if the energy is released to the surroundings as kinetic or absorbing in that kinetic energy. It really depends on if I'm endothermic or exothermic. So let's go ahead and look at the next page. And hopefully at the top of the next page, we'll see a term that we're a little bit familiar with. First off, as a throwback, remember that energy is required to break bonds or IMFs. And when I say energy, I'm referring to taking in energy from the surroundings, taking in that kinetic energy. If I want to break apart these two atoms from each other, I'm going to have to take in some kinetic energy from the surroundings to hold them apart, so I have that potential energy now to keep them apart. However, if I let them reform those attractions, then that's going to release that kinetic energy into the surroundings. So when we were saying energy is required or energy is released, that is referring to what is coming in from the surroundings or being released to the surroundings. And if you think back a few units ago, we talked about a term. That term was takes to break, freeze to form. It takes energy to break those attractions apart. It frees energy when they reform. We talked about that pretty extensively when we talked about, say, lattice energy or bond energy. We're going to revisit both of those within this unit. Lattice energy is that energy it takes to break apart an ionic structure. Bond energy is the energy it takes to break apart a covalent structure. So we will be utilizing some of those numbers as we get further along into our calculations in this unit. However, here's the thing. Sometimes I'm doing a combination of both of these. Like, let's say I have some sort of reaction. I might need to break some bonds apart, but then I might need to reform some new ones. And so depending on which of these values is larger, your overall change can either be endothermic or exothermic. So we really kind of have to compare how much energy are we taking in to break and how much are we freeing back up when the things reform. So we have to compare those differences. So to kind of see an example of that, this is a very very simplified version of a potential energy profile or potential energy diagram. We kind of saw these last unit already. We talked about these when we dealt with kinetic mechanisms, and the fact that we start with our reactants over here and they have a particular potential energy. Our products also have a particular potential energy. And in this case, in order to get from reactants to products, two things need to happen. Number one, I need to break what I have apart. The bonds that are existing need to go. However, I then want to reform my new bonds. And I'm not addressing here the exact mechanism that takes place. So this may or may not be my activated complex. We don't know. But just to simplify things here, I just want to compare the fact that I've got to put in some energy to break. I've got to release energy when these reformed, but I notice that those two amounts are not the same. For this particular example, the energy required to break the bonds is a lot less than the energy that's released as the new bonds formed. So even though both of those processes are happening, because the energy that it takes to break is less than the energy that I free when I reform, overall we would say that we have an exothermic process. Now there's one other thing I want to point out about this diagram. A lower potential energy is considered more energetically stable. So these products that we see here, because they're at a lower potential energy, they are considered more energetically stable than the reactants that I had originally over here. So that would help to drive this reaction to completion. And one of the things that we talk about when we get to Unit 9, where we talk about Gibbs energy and entropy, is that we talk about being thermodynamically favorable. And one of the things that we'll talk about is the fact that if we're going to a lower potential energy that's more energetically stable, that is a favorable process, that is typically more likely to happen. So again, for an exothermic reaction, we could say that the products are more energetically stable than reactants. Obviously, if the opposite situation here is true, then that would mean I could have an endothermic reaction. So on the next page, we have a chart that kind of compares endothermic and exothermic. So let's go ahead and go through that together. So you notice on the top of this chart, we have endothermic. Here we see kind of a more traditionally shaped potential energy diagram. They did not address the mechanism that's taking place here. So this is assuming a one-step mechanism. Obviously, you might have multiple hops here if you had a mechanism, or you might even have, a lower activated complex if you added a catalyst or something like that. So this is just kind of referring to a very basic potential energy profile diagram here. And what we see on this particular diagram is that the energy it takes to break, aka that activation energy, is a lot greater here than the energy that I release when I reform my products here. And so the energy needed to break being greater than the energy freed when formed means that overall energy must be entering this system. I need to gain some energy from somewhere to get the products to have a higher potential energy than the reactants. Where is that energy going to come from? It's going to come from being transferred from the surroundings as kinetic energy into the system as potential energy. And so again, the problem is that I cannot feel that potential energy once it's entered the system. All that I'm going to be able to feel is the fact that we're intaking that kinetic energy from the surroundings into the system. So that's going to play a role here when we talk about how this system feels. Next, we could say that energy is absorbed or gained by the system. And so we can see that here, that overall, as we went from reactants to products, there was a gain of energy that occurred. Observationally, this is the one that always catches everybody. The system will feel cold to the touch. And I know some of you are thinking, how in the world is that possible? Well, think about it. The problem is here is that I'm transforming energy into a different form that can't be felt. It's not that just I'm, adding more kinetic energy and so things are getting hotter, but I'm taking kinetic energy and transforming it into potential energy in that reaction that cannot be felt. So if I put my hand up to that reaction, all that my hand can feel is that kinetic energy is being taken from my hand, from the surroundings, and being transformed into potential energy that can no longer be felt. All my hand feels is that loss of kinetic energy. And so therefore, that system will feel cold to the touch. That also means if I was to put a thermometer into that process, the same thing would be happening to the thermometer. It's part of the surroundings. It would be having kinetic energy stolen from it in order to transform it into potential energy within that reaction. And so therefore, the temperature will initially decrease as the kinetic energy is removed from the thermometer itself. Now, I will mention this. I did put initially decrease because eventually over time the system would reach thermal equilibrium, and so we would see that the temperature would eventually level out. However, we would see that dramatic temperature change occur right off the bat as the reaction first got going. Now, numerically, if we were to report a number with this process, we would need to put a positive sign with it. Again, that energy was gained overall. That kinetic energy was taken into that system and transformed into potential energy. I can't sense that potential energy changing, but I can sure sense that gain of kinetic energy into the system due to the loss that was felt by the surroundings. So, because the system gained that energy, I'm going to call that a positive number of either joules or kilojoules, and typically we put per mole of reaction. We're going to talk more about that term here in just a little bit. Also, we would say that the delta H value is greater than 0, so that's another way of saying that it's a positive value. As far as writing a reaction itself, I could say that heat could be considered a reactant, so I could place the heat on the reactant side in a reaction, and the reason for that is because the heat as kinetic energy along with the potential energy of the reactants would combine together to be the potential energy of the products. So that's where that energy is being conserved at. The total of the kinetic energy and the potential energy of the reactants together gives us that potential energy of the products. Now, obviously, exothermic is almost exactly opposite. Okay, so for exothermic, here the energy it takes to break is a lot less than the energy released when I reform my bonds. And so therefore, overall energy is exiting the system if it's exothermic. We are transferring from the system as potential energy, releasing it to the surroundings as kinetic energy. So now what happens is as that kinetic energy leaves, now it can go to the surroundings, say, to my hand, and my hand overall will end up feeling warm. We could say that that energy is released or lost by the system into the surroundings. And so what that means for our temperature is that our temperature would initially increase. If I had a thermometer present in an exothermic reaction, I would notice that the temperature would increase on it. Now, numerically, because it was lost by the system, we would give this a negative number of kilojoules per mole. So be very careful there. Temperature went up, that's a positive change, but we would say that the heat change by the system is negative. Or you could say that the delta H is less than 0. That's another way of showing that it's a negative value. Also, now we could put heat as a product to show it's being released. And so what would happen is that lower potential energy of the products in combination with the kinetic energy that's being released would give us the potential energy of the reactants. So again, that's showing how that energy overall was conserved. Now, let's look how we could see this illustrated in an actual reaction. So go ahead and flip the page with me to a couple of examples on our very last page of these notes here. All right, so it gives us here that the complete combustion of methanol forms carbon dioxide gas and water vapor, along with releasing 715 kilojoules of heat per mole of methanol. By the way, anytime they give us some sort of hydrocarbon, some sort of fuel, and they tell us a heat that's released per mole of that substance, that is referred to as the delta H of combustion. And we're going to talk more about that symbol on another class period. Now, what I first would have done is to write a balanced thermochemical equation. I would have first just written my regular balanced equation. So that's what I did. I have my CH3OH plus my O2 yields CO2 and H2O, and then I went and balanced it with my coefficients. Now, here's something that's interesting on this one. When I balanced that reaction, that ended up having 2 moles of methanol. However, you notice up here, these 715 kilojoules of heat per mole of methanol would just be for 1 mole. So since our reaction has 2 moles, that means for this reaction, I would need to double that value. Here's the other thing. It says that that heat was released. If it is being released, that means that heat is exiting. And so therefore we would say that this is an exothermic process. So if I wanted to pick what side of the equation my heat goes on, I definitely want to put that heat on the product side of my equation. So you notice here I put and, so that plus is not a positive, that plus is just and 1,430 kilojoules. So be really careful. If I had put that 1430 kilojoules here first, I wouldn't have needed any kind of sign in front of it. When I put the heat as a reactant or a product, I don't include a sign. That is just an and symbol for that particular process. Now, when I report the delta H of reaction, I want to report it per mole of reaction. And what we mean by mole of reaction is one of these balanced equation reactions. So for one of that overall reaction, I released 1430 kilojoules. Now, when I write the heat all by its lonesome like this, I want to indicate if it's endo or exothermic. And so I do that by putting that negative symbol there. You notice I didn't need to put that sign when I placed it as a product because that shows it is an exothermic process. But here I'm just writing the heat by itself to show that it's exothermic. I need to put that signage there. So then it says, is the reaction endo or exothermic? Well, of course it's exothermic. We already said that it was because the heat was released. So what that means is that heat is transferred from the system to the surroundings. I had a whole bunch of potential energy here, but I must have had less potential energy here because then I released that kinetic energy to the surroundings. So it asks, would kinetic energy be absorbed or released? Of course, it would be released because we're transferring it to the surroundings. My hand would be able to feel it at that point. It would go to the container. It would go to a thermometer, to all those things. If I wanted to sketch a sample potential energy profile, again, I don't know what the mechanism is, so I'm just going to assume kind of a one-hop situation here. But the key thing is I would want to put my products 1,430 kilojoules below wherever I started at for my reactants. Here, the reactants would contain more potential energy, but that means that my products would be more energetically stable. As we already said, because I'm releasing that heat to the surroundings, my hand is part of the surroundings. And so if I put my hand up to that container, it is going to feel hot to the touch. And that also means that if I put a thermometer to it, the kinetic energy would be released to the thermometer, to part of the surroundings. And so therefore, the temperature on a thermometer recording would increase as well. All right, here's what I want you to do. I want you to take a moment, pause the video, and see if you can answer those same questions for this next example. So go ahead. Pause the video, try them out. Did you try them out? Did you pause it? I hope you did. Let's go ahead and check them really quick. So here, conveniently enough, when I wrote my balanced reaction, everything had a coefficient of 1. So when they told us that 109 kilojoules of heat per mole of CaOH2, the good thing is that that was okay to write in my reaction because I only had 1 mole here. It said addition And so therefore I put my heat as a reactant. Now I did put this at the front. You could have put it behind the CaOH2 as long as it was on the reactant side. It really didn't matter. Since I put it first, again, I didn't put any kind of sign on it. If you put it second, obviously you would have the and symbol there, but not a signage in the reaction itself. My delta H of the reaction then, I would report a positive 109 kilojoules per mole of the reaction, per one of these reactions. It's going to absorb in that 109 kilojoules. The reaction would be endothermic because, again, we're adding in that heat. So that means heat was transferred from the surroundings into the system. That kinetic energy plus the potential energy here is combining together to give me the potential energy of that products. And so that kinetic energy is being absorbed in and then transformed into that potential energy. So my sample potential energy profile should overall go up. I should see my products higher than my reactants. So here, products contain more potential energy, but that means that the reactants were actually more energetically stable. Would the reaction feel hot or cold? Well, again, if I'm taking in that kinetic energy and transforming it into potential energy that can't be felt, all that my hand can feel is that we're stealing that energy from my hand and putting it into that substance that can no longer be felt. So your hand is going to feel cold due to that loss of heat. Our temperature of our reaction would decrease if we measured it with the thermometer. All right, I hope we're feeling confident about the differences between endothermic and exothermic processes. If you have any questions or need any help, please feel free to email me. Bye, guys.